In this video, we're going to talk about collisions in two dimensions. So the picture here explains exactly how a collision in two dimensions takes place. So you have a mass m1 that is moving with some velocity v1 initial, and a mass m2 that is at rest. So when m1 collides with m2, notice that it gets deflected through an angle theta. Meanwhile, m2 gets deflected through an angle called phi. So what we can do is that we know that so we can apply we assume that this is an elastic collision. So if this is an elastic collision, it means that I can apply the conservation of momentum in the x and the y direction. So because the momentum is a vector, I can say that the total momentum in the x direction before must be equal to the total momentum in the x direction after, and the total momentum in the y direction before must be equal to the total momentum in the y direction after. So before, because m1 was moving in the x direction, I can just say that m1 v1 initial is equal to m1 v1 final cosine of theta plus m2 v2 final cosine of phi. So again, if you look at this picture here, so I'm taking my v1 final and I'm breaking it up into x and y components. So the x component is v1 final cosine of theta, and the y component is v1 final sine of theta. Now if you look at m2, notice that the x component is positive, is v2 final cosine of phi. The y component is negative, is going to be negative v2 final sine of phi. So when I apply my conservation of momentum in the x and the y direction, I obtain my first equation right here. Now in the y direction, notice that before, because m1 was moving just in the x direction and m2 was at rest, it means that there is no momentum in the y direction before. And after, I have my m1 v1 final sine of theta, which is this contribution right here, minus my m2 v2 final sine of phi, which is this contribution right here. So I obtain my equation number 1 and my equation number 2. And then if we assume that there is no external forces acting on the system, it means that the total kinetic energy before must be equal to the total kinetic energy after. And so I can write this equation right here. So generally, whenever I have a collision in two dimensions, so basically it's going to give me m1 and v1 initial and m2. Then it's going to ask me to calculate my v1 final and my v2 final, as well as the angles theta and phi. So again, before we solve any problems, so when we solve problems involving two-dimensional collisions, so again, the very first thing is that you want to apply your conservation of momentum. So you say your p1x is equal to p1x in the initial direction. So p1x initial must be equal to p1x final, and p1y initial must be equal to py final. So you just apply your conservation of momentum, and then if the momentum is an elastic collision, then we can write down one more equation for conservation of energy. All right. So now at this time, let's look at example number 9.8. So at example number 9.8, we're going to look at the collisions at an intersection. So we have this picture here. So we have a car. So a 1,500 kilogram mass car that was moving in the I direction. So this was moving in the east direction, is going to collide with a 2,500 kilogram truck that was traveling north at a speed of 20.0 meters per second. And then it's going to ask us to find the direction and the magnitude of the velocity of the wreckage after the collision, assuming that the vehicles stick together after the collision. So this picture illustrates what is going on. So you have, this is my m1, this is a car moving in this direction, this is a truck. before, and then after the collision, the two cars get stuck together and they move with some final velocity v final. So I want to calculate my v final, and I also want to calculate my angle theta. So when I set up my equations, I know that the change in momentum in the x direction has to be equal to 0, and the change in momentum in the y direction has to be equal to 0. So in the x direction, I can say that m1 v1 initial must be equal to m1 plus m2 v final cosine of theta. And then in the y direction, I can say that m2 v2 initial is equal to m1 plus m2 v final sine of theta. And so if I look at these two equations here, because if you divide equation number 1 by equation number 2, notice that the m1 plus m2 is going to cancel. So m1 plus m2 here is going to cancel. So you can get this equation here. And so if you just, by substitution, you can find what this angle is. So the angle is going to be 53 degrees. So now that I know what this angle is, I can substitute into one of these equations to calculate the magnitude of my v final. So by substitution, I can say that my v final is equal to m2 v2 initial over m1 plus m2 sine of theta. And if I plug in everything, I end up getting a value of 15.6 meters per second. So again, this is an example of an inelastic collision. All right. So now let's look at one example here that is an example of an elastic collision. So this is an example of a proton-proton collision. So again, we have the picture here on the right side. So you have a proton of mass m1 that is moving with some velocity v1 initial, and then you have a proton of mass m2 that is at rest. So when m1 collides with m2, notice that m1 is going to get deflected in this direction, and m2 gets deflected in this direction right here. So it tells us that the incoming proton has an initial speed of 3.5 times 10 to the power 5 meters per second and makes a glancing collision with the second proton as shown in the figure. It says that after the collision, one proton moves off at an angle of 37.0 degrees to the original direction of motion, and the second deflects at an angle of phi. Find the final speeds of the two protons and the angle phi. So this is the problem that we're going to solve. So this is before, and this is after the collision. So after the collision, you can see that one of the protons is going to take off at this angle here, and I know that theta is giving us 37.0 degrees in the problem. So what I want to calculate is that I want to calculate v1 final, which is the velocity of proton number 1, and I also want to calculate the v2 final, which is the final velocity of proton number 2, and I want to calculate this angle phi, which is the deflection angle for proton number 2. So for me to solve this equation here, I need to apply conservation of momentum in the x direction. So this is my equation number 1. Conservation of momentum in the y direction. This is my equation number 2. And then the third equation comes from the kinetic energy. So notice that here, because a proton, so in this problem we're talking about two protons, so the masses are the same. So because the masses are the same, I can just write the kinetic energy conservation using this equation right here. So because the masses are going to cancel, I can say v1 initial square is equals to v1 final square plus v2 final square. So in this problem, we know what v1 initial is, so this is given. We know what theta is, so theta is giving us 37 degrees. And so we need to solve these three equations to get v1 final, v2 final, as well as the deflection angle phi of the second proton. So basically we can rearrange this equation like this. So again, you can we can rewrite equation number 1. So from equation number 1 here, you can just rearrange this equation and write your v2 final cosine of phi is equals to that. And then from equation number 2, you can write your v2 final sine of phi is equals to this. And then if you take the square of these two equations and you just add them up together, you get something that looks like this here. And then finally, with some simplification, we obtain equation number 4 right here. And then with a little bit of rearrangement, you can obtain your equation number 5. And then solving for that equation, you get your V1 final, which is 2.8 times 10 to the power 5 meters per second. Now, since we know what V1 final is, we can go back to our kinetic energy equation and plug in that value to get my V2 final. And if I do that, I get 2.11 times 10 to the power 5 meters per second. And then if I go back and just use one of those conservation equations, that will help me to get my deflection angle phi for my second proton. And if I do that, I get a value of about 53.0 degrees. So again, this looks complicated, but it's not really complicated. It's just solving 3 equations to get 3 quantities.